I think we're good? Yeah, okay. Okay, great. So I was asked to give a review on where we stand in with gravitational lensing. Can everybody hear me okay? Yeah? All right. So that's essentially what I'm going to do. So gravitational lensing, normally you can classify it into regimes. There's weak lensing and strong lensing. I'm going to talk about weak lensing in particular. Both of them constrain the accelerated expansion of the universe and the nature of dark matter. But most of this talk will be about constraining the growth of structure and the accelerated expansion. We have a couple of surveys that are finishing. They completed data taking and they're processing their final data. So those are KITS, DES, and HSC. And we're already starting the stage 4 surveys. So Rooming Observatory already taking data as well as Euclid. And then hopefully to be launched soon, the Roman Space Telescope. Okay, so that we're all on the same page, what is gravitational lensing? Well, if you have light from a distant galaxy coming to the observer, then light will follow the geodesics of space-time, and then if it encounters some energy density along the way, the path will be distorted from a straight line, which means that in the strong regime, you will see two lensed or more lensed images of the galaxy, and in the weak regime, you will just see a slight change of shape of this galaxy. In the weak regime, this is what this might look like. You have an overdensity that is, for example, a galaxy cluster, and the shapes of galaxies will be tangentially distorted around the center of this overdensity. So these are all the background galaxies whose light is traveling through or nearby this overdensity. These distortions are very small, so they're roughly percent level, so you need to catch them statistically, which means that you want to have as many galaxies as you can in your survey in order to catch these 1% distortions. This is why we make the compromise of getting photometric redshifts instead of spectroscopic redshifts, because we don't have enough galaxies if we try to get spectra for all of them. Okay, this is the typical patterns that you get, this tangential distortion called E-modes. These ones, these radial patterns can arise due to another phenomenon that I'll discuss in a little bit. And then these B-mode patterns, normally people think of them as an indication that your survey has some systematics due to the masking or PSF being incorrectly modeled or something like that. So every single survey will go and look for these B-mode patterns and say, okay, if I have them, then there's a risk that I'm doing my measurement incorrectly and I need to go correct for it. I would argue that in this era of precision lensing, maybe this is not such a good idea anymore, but okay, we can discuss that in a little bit. Why does lensing constrain cosmology? Well, it's sensitive to this distance ratio between the distance from the observer to the lens and from the observer to the source, which appears here in the prediction of how much convergence, how much lensing distortion you will get in your galaxy. So that probes the distance redshift relation. And then at the same time, the presence of this density that is causing the lensing probes the growth history and the matter distribution. Now, if you want to probe the growth history as a function of time with the hope to constrain the evolution of dark energy, then what you do is you want to bin your data. So you place your galaxies in redshift bins, and then you try to measure the how much lensing you have in this bin, in this bin, in this bin, and also the cross correlations between how much lensing you have in this one and this one, for example, because there's part of the lensing of this galaxy that's coming from the structure here in front of this other one. So they will share some common lensing, and that's why you get the cross correlation as well. Okay, so that's what we would call cosmic shear. It's a correlation of lens shapes with lens shapes. But there are other cross correlations or autocorrelations that we use in this business to try to constrain the cosmological parameters. So now it's very common to perform what we call the 3x2 point correlations, which is not only the cosmic shear, but you add the galaxy-galaxy lensing, so the correlation between galaxy positions and lens shapes, and you also add the galaxy clustering, so positions. Normally, this is not the spectroscopic clustering that we've been talking about throughout this week and past weeks. It usually refers to flux limited or color selected sample that has very good photometric redshifts for which you have a very high number density in your survey. So examples from DES are Red Magic or Maglim for this particular measurement. But you could combine with the spectra. We'll see that that can also happen. All right, so the distance redshift relation lets us probe W of Z. And the hope is that if we have an understanding of what this equation of state, how this equation of state evolves with redshift, then we might be able to map that into different physical theories and then try to figure out what is the origin of this dark energy. And then by adding this sensitivity to the growth history, either from lensing itself or also from adding the clustering, then we're able to probe modifications of gravity. We sometimes do that in a parameterized way through mu and sigma, for example, or specific theories of modified gravity, Horndersky by gravity, or non-local gravity. These are, for example, the priorities that we set for ourselves in the context of analyzing the Rubin data, just because we don't have the people power to do every single possible theory. Okay, but all the current constraints are mostly focused on growth. So on this combination of sigma 8 and omega matter. So this is what we currently best constrain from the lensing data. And this is the combination of parameters that we use to assess whether there's any tension with the CMB, because the CMB is telling us what this should be from the high redshift constraints, and then we are getting a value from the low redshift, and then if there's a tension, then something happened in between. So this is the space of surveys that do gravitational lensing. So these are the stage 2 surveys already far in our past, let's say. These are the stage 3 surveys whose cosmological results you're seeing on the archive in the past few years. So KIDS is already pretty much done. DES, the latest results are the year 3 results, but hopefully the year 6 results will come up soon. And then HSC, the latest ones are year 3, but then I think there's one more analysis to come from this. And the stage 4 ones are already starting. So you can see that the area increases as well as the number density. So better CCDs and better telescope technology allows us to probe wider areas faster, so we can also go deeper faster, and that means that we get more galaxies over a larger area. So we're at the level of getting like 100 million galaxies for stage 3. This is a typical number that we would use nowadays to constrain cosmic shear. But now for LSST and Euclid, we're talking, and Roman, we're talking about 1 billion, roughly. Okay, I said we use photometric redshifts, so you can see here the colors representing what filters these surveys observe in order to constrain the photometric redshifts. So most of them observe in UGRI, sometimes UGRIZ. KIDS is a little bit particular because it got an extension to the near infrared thanks to the Viking data. So that's nice because we get 9 bands, and that allows us to get a little bit better redshifts. All right. So now I'm going to give you an overview of where we stand in terms of the stage 3 results of these surveys before we progress to what the challenges are for stage 4. Okay. I'm going to do this mostly through plots from some of the KIDS paper, just because that's the one that I'm involved with. But I'm going to show you all of them, HSC and DES as well. Okay, so the last release of the KIDS cosmic shear analysis is the KIDS legacy. This is the final one. There's no more cosmic shear after this. There will be 3 by 2 points, but cosmic shear, this is it. Okay, takeaway, no tension with Planck. Okay, there's no tension with Planck whatsoever. Why is there no tension? If with KIDS 1000 we did have a tension that was, you know, at the level of 3 point something sigma. Well, many things have changed. Main driver has been the increased area and adding a 6 tomographic bin. So just statistics have helped a lot, but there are other things that helped. So in going from here to here, we got better image simulations. Then going from here to here, We did better photo C calibration. And then from here to here, this was just the technique of getting the photo Cs. And then from here to here, it was adding much more, much bigger calibration sample for a photometric redshifts. So you can see that only those things drove us from minus 3.75 sigma from Planck to minus 1.6. Then for the legacy analysis, so this is the old KITS 1000, then from the legacy analysis, if you apply the analysis pipeline that we use for legacy in the KITS 1000 data, then this is what you get with 5 bins. If we go from 5 tomographic bins to 6 tomographic bins, so going further in Redshift up to Redshift 2, then we constrain S8 a little bit better. Now we're at minus 1.4. And then in our fiducial legacy analysis, which is now much bigger because it's 1350 square degrees, now we get a tension that is minus 0.7. So from here to here is just more area, okay? Okay, so no tension with Planck. This is the list of things that we've improved since KITS 1000. And there's nothing in the modeling that has really changed. It's all really statistics and photo C. Yes. Yes. It is a coincidence. You should have been there at the unblinding. It was very interesting. Yes. Okay. Okay, what about results from the other surveys? So here we have Planck in red, so S8 omega matter. Here we have Kids Legacy, and then we have DES year 3 and HSC year 3. We're pretty much all consistent. You can see the tension with Planck is very little, up to 2.3 sigma for HSC, but it really depends on how you quantify your posterior and where you put your maximum a little bit. So yeah, it's not really not so much of a tension anymore. And notice that here we have the S8, but here we have this capital sigma 8. So this is just the same thing, but with a slightly different index, just because we're most sensitive to this, to actually this index. But it's okay. It still constrains the same cosmological parameters. All right, everything's in agreement, so you can think of combining. So this is from Benjamin Stolzner's paper. So again, here we have Planck, and then we have KITS, DS year 3, and then we have the combination of KITS Planck CES, and then if you combine with DESI and supernovae, then this is where we are. So it's like right on top. Okay, so what about opening up the parameter space? So that's a little bit difficult right now. We're not super sensitive yet to W0 WA. That will come in stage 4. But still, I mean, we can try to do this. So this is from the dark energy survey. If you want to open up the parameter space, you really need more probes. So now I'm talking about 3x2 point and not cosmic shear. So these are their constraints from year 3 on W versus omega matter, consistent with -1, but you can see that the error bars are pretty big. This model, if you think about, okay, is this model preferred compared to lambda CDM? The answer is no, and the same thing happens for 3x2 point combinations for the KITS 1000 data. In that case, it was not preferred either, and the constraint was very close to -1. We don't yet have this for the KITS legacy, so stay tuned because more stuff is coming out at some point. So are there still tensions? So we've been talking about the galaxy-galaxy lensing problem, where galaxy-galaxy lensing is low. So Emmanuel showed yesterday some results from KSC, which I'll go back to talk about in a little bit. But the idea is that if you try to measure galaxy-galaxy lensing through the delta sigma profile of this, the matter around the lenses at very small scales, then you get some discrepancy with Planck, right? So Planck here is the pink, And the green are HC lensing measurements, and no, sorry, green is DS plus kits, and orange are HC. And this is low. So why is it that galaxy-galaxy lensing is low at the very small scales? This seems to point to a different problem. There are possible solutions. So already Emmanuel yesterday talked about the role of baryonic effects in suppressing the power spectrum at small scales. So this is partly what we think is going on, but he showed that that only gets you halfway. So if you really want to increase the suppression and match the data, there are many things that could be going on. So this is from a really nice paper by Jonas Chavez Montero, where he looks at building an HOD in Illustris TNG, in TNG 100, I think. And then he tries to understand what are the different phenomena that are leading to a discrepancy between the assumptions of regular HOD models that we use to analyze the data with what he sees in the hydrosims. And there are many different things that play a role, but just to save you some time, the ones that are most important are, aside from the baryonic effects that are half of the effect, are assembly bias and satellite segregation. So the fact that satellites, red satellites in particular, do not follow exactly the lensing, the NFW profile of the halo, but you might have some more closer to the inner part of the halo, while you have bluer stuff in the outer parts of the halo. So this is what he calls satellite segregation, and this seems to be playing some role here. So is there still a tension in lensing? Well, it looks like we might be on the way to resolve this, at least for current data sets, but we'll see what LSST, Euclid, and Roman have for us. Okay, so what can we expect for stage 4? The constraining power will be huge. This is from forecast for the LSST desk for how rooming observatory cosmology will do in year 1 of the survey versus year 10 of the survey. So year 1, we're talking about data that is coming in 2028, beginning of 2028, roughly. So we're not so far from that anymore. In fact, the survey itself should start at the summit before the end of this year, so in just a few months. Right now, there's a downtime due to engineering activities at the summit, but the survey should start around the end of the year. Okay, so for LSST, we plan to combine several different probes. The lensing one is this one, the dark blue one that you can see will constrain W0 WA very well, but then, okay, so with the other probes, we hope to break a little bit the degeneracy here, because supernovae, for example, are going in a different direction. And then with year 10, we are hoping to achieve around 10% constraints on both W0 and WA now. Okay, so that's the plan, but that's an enormous constraining power, which means that there will be some challenges. And so I'm going to tell you a little bit about some of the challenges that we face. I'm going to, wait, okay. So I'm going to talk a lot about the nonlinear regime, because weak lensing is very sensitive to the nonlinear regime. There's a lot of information to be extracted there. So if you cut scales, you really lose a lot of constraining power on S8, omega naught, omega A. So we really want to see if we can try to get these scales in. In the 3x2 point, when you combine with clustering, then okay, you get a little bit more into the intermediate regime. So then it's not super crucial to go fully nonlinear. But if you want to probe delta sigma, then yes, then you need to go fully nonlinear. Okay, so these are some of the systematics that we worry about. So first, the alignments of galaxies. So the fact that galaxies are not only lensed, but they're also aligned by the large scale structure. So their tidal processes, accretion, mergers. We're not sure exactly what drives this, but it turns out that galaxies end up pointing towards each other in the large scale structure, and that's an intrinsic effect that correlates with the large scale structure and we cannot get rid of. So we need to model it. It has the opposite sign to lensing in general, so it generates E modes that have negative signs, so it tends to suppress your lensing signal. Then we have photometric redshift. So I already said a little bit about that. The fact that we only observe the galaxies through a bunch of filters, so UGRIZ, for example. And what that means is that we can't capture the whole spectrum, and our knowledge of the redshift is a little bit limited. Then we have baryonic effects, so the gastrophysics, the fact that where the gas lives in the large scale structure seems to be creating a problem for lensing, because we used to model the matter power spectrum as dark matter only, but that's no longer the case, because if you have a 1% constraining power on the power spectrum, then a 20% suppression from the gas is definitely something that you need to consider. And if you're worrying about 3x2 point or 2x2 point instead of just cosmic shear, then of course you want to be able to model nonlinear galaxy bias. And there are many other things that we worry about that I will not touch upon. Magnification is going to become very prominent in stage 4 surveys. How well we can calibrate our shapes, blending because we're going deeper, so all the sources start to merge with each other. And the time it takes to run a sampler. That's also one concern. It seems like that is under control, but okay, there are always ways to improve that and try to get our results faster. I will not say much about galaxy bias because it's already been touched upon, and there are many people here in this room that know much more about this than I do. So I'll touch upon some of the other ones, and let's start with alignments. Okay, so galaxies are aligned across the large scale structure. It's normally massive red galaxies that we see are most aligned with each other. For the blue galaxies that tend to live in less dense environments, there's very little evidence that they aligned, although from theory it could be expected because of the way that they acquire their angular momentum. It's not ruled out that they might be aligned as well. Why is alignment a contaminant? Well, when you measure the autocorrelation of galaxy shapes, for example, in cosmic shear, then you get the autocorrelation of the lensing. So this one, GG, capital GG, or what I call C cap over here. But then you also get the cross correlation between lensing and alignments. So a galaxy that is aligned by some large scale structure is correlated with one in the background, because it's the same large scale structure that aligns the galaxy that is lensing the other one. And this is the dominant source of contamination, this lensing cross alignment term. You can also get alignment, so the shape-shape correlation. We also have the alignment contribution that is more prominent at low redshift. And generally, we don't have a lot of lensing constraining power at low redshift, so this one is a little bit less important. Okay, what do we do about this? We model it. It's very hard to get rid of it, so people have tried. There's some techniques, I'll show you some, that allow you to try to remove it from your data, but they haven't yet fully matured, let's say. So the default procedure is to model this thing. You model either with some linear model or what we call the NLA model, which is just linear theory with the nonlinear matter power spectrum plugged in. That has one free parameter. Or you can do perturbation theory or EFT. So this other model is quite popular. For example, the DES papers use it a lot. This has between 2 and 3 free parameters, depending on the implementation. It's based on standard perturbation theory. Then we have EFT of galaxy shapes, so something that we've been working on with Zvonimir and Thomas. Stephen also has an LPT version of this. That has between 6 to 8 free parameters, up to third order. You can also use a hybrid approach, so combine nonlinear displacements of the matter field in embodied simulations with this EFT. And that also gives you a very good handle on alignments, 2 free parameters only. If you want to go fully nonlinear, then your only option really is the halo model. There are fast mocks as well, but there are no emulators for now, as far as I know. But this is something that the field is slowly moving into. So how well do these models do? So this is a comparison that we did with Francisco Mayon in embodied simulations. And here you can see all these models: linear alignment, nonlinear alignment, then this hybrid model called Himalaya, or EFT, one a reduced version that only has 7 parameters, and then the TAT model. And you can see how well the models fit the data. Here's the chi-squared. Here's your one threshold. This is the figure of bias, and this is the figure of merit. And well, what you see is that if you look at high fidelity, large number density of halos in an embodied simulation, you quickly see that these linear models or this NLA model stop working very soon at k of roughly 0.3. And then with the EFT, you can push further, and with Himalaya, a little bit further, up to 0.7. This is still far from where lensing gets most of its constraining power. So whether we're going to be allowed to use these models for the stage 4 data, we're still not sure. I think the answer is only if we cut scales a little bit. So I'm envisaging that we'll do, both things. We'll cut scales and use some of these physically motivated models, while at the same time we do another analysis where we try to go fully nonlinear and use the halo model. So probably both things will happen, and we'll see how robust we are to this in the future. Yes, these are halos. Yes, these are halos. Yeah, we also have now something like this for galaxies as well from Flamingo, but I don't have that to show you yet. Yeah. Okay. All right. So we have the models. How do we get priors for the models? So we get priors through direct observations for either spectroscopic or photometric samples that have very good redshifts. So that's what we try to do. So this is a compilation from some work that we did with Christos Georgiou a year ago, roughly, where we're looking only at red galaxies, and we look at how strongly they align. So this is just the linear alignment model. How strongly do they align as a function of the luminosity? And what we find is that red galaxies tend to be more strongly aligned if they're more luminous. Okay, so there's some kind of power law dependence here with luminosity, which translates into roughly a power law dependence with mass. Might be something weird going on at very low mass for the satellites, but okay, I'm going to avoid that discussion for now. And so those are the red galaxies. What about the blue? So for the blue, these are results from Jared Siegel from some recent DESI analysis with some DES kits and SDSS shapes. Generally, if you take the bluest galaxies in DESI, you find that their alignment is consistent with null. If you start relaxing that criterion for, what's the fraction of blue galaxies that I have in my sample, then you start seeing some alignment. But the bluest galaxies are generally consistent with null. So people think that, okay, possibly the blue galaxies we can ignore, but we're not super sure yet whether we should do that. So you can fold in these priors into your cosmic shear analysis. So this is an example of that. So this is the KITS cosmic shear results. Split, so the constraints from splitting your data into red and blue galaxies. And you can see that nothing changes pretty much. Also, depending on how you select, you say, okay, what's red and what's blue, really nothing changes. So we're pretty immune right now to these possible variations in how much alignment we have. And same thing for DES. So this is, let's see, so this is the shaded, the dashed one is the DES full data with the NLA model, scale cuts and no feedback. So that's basically their fiducial. And then if you just use the blue galaxies and assume they have no alignment, then of course you get tighter constraints, but it's still consistent with what you had before. Are there blue galaxy alignments? Well, I don't know. So if you look at hydrosims, and this is work that one of my PhD students is doing, Marlos van Heukelom, you look at different hydrosims, you try to select blue galaxies all in the same way, either by their color, G minus R color, or by their dynamics, which we think is more important for determining the galaxy alignment. Then anything can happen. So in TNG and EGO, you get positive alignment signals, meaning that these galaxies are aligned and they're aligned pointing towards overdensities. And in Horizon AGN, you get a negative signal, so they're aligned tangentially around overdensities. And this is all at redshift 1, which is, well within the realm of stage 4 surveys. So this is a problem. This is big enough that I might worry about completely nulling out the blue galaxy alignments for stage 4. So I don't think we should do that in the future. But okay, it's unresolved because how do I understand these conflicting results between the hydrosims is very difficult. They use different techniques, different numerical techniques to come up with these galaxies. And unless we start from scratch and try to do a very deep comparison between these hydrosims, I don't think we're going to resolve this. Yeah, so there's the DESI ones that I showed before, and then there's some stuff from HSC, ELG that constrain as well. But the error bars are still not tight enough that I must just say, okay, I'll set it to 0 for stage 4 lensing. Yes, at low redshift it goes away. Yes, in the hydrosims, correct. Mm-hmm. Okay, it's not all bad news because there's a lot of new physics to learn from alignments, just from the massive galaxies. These are a bunch of things that you could do from them. And these are the papers that have looked into all these things, the theory papers that have proposed that you could use alignments to constrain all of these particular physical processes. Some of them have been verified in simulations, that the theoretical predictions make sense, and we do see the effect in simulations. And some people are moving in the direction of actually using the data to constrain some of these processes. So I think this one is super interesting by Toshiki Kurita, where he looked at primordial non-Gaussianity from alignments directly in the BOS data. So it's it's percolating this way, which is nice. All right. How much time do I have? 10 minutes? Okay. Okay, so let's talk about baryons. We already heard from Emmanuel yesterday a little bit about this, about for TSC and KSC. I'm going to show you some complementary stuff. Okay, so baryons suppress the matter power spectrum at small scales. This is the 1% precision that we hope to achieve with stage 4 surveys. So this is way too bad to be disregarded. And this suppression comes mostly from the distribution of the gas, as Manu said. And the hydrosims don't agree on how much suppression you should get. But if you restrict to K of 0.5 roughly, you get them all to line up in a single relation, which is pretty striking. So the suppression of the power spectrum of K of 0.5 can be parameterized by a single parameter for all the simulations, despite them being quite different. Why is this? Well, my hypothesis is that if you're staying at very low K, then you can probably treat this perturbatively, and then there's just one parameter that you care about. Okay, I haven't shown that that is the case. I'm trying to, but but I think that's probably the situation we're in. When you move away from K of 0.5 and go to higher Ks, you can go look at this paper. I think they have some plots for that. Then this starts to break. Okay, this relation starts to break, and you need more than one parameter to describe the impact of baryons on the matter power spectrum. What do we do about this? Again, we can't get rid of it, so unless we cut scales, which is one option, but then you lose data. So we model it. There are a bunch of tools that you can use to model this. So there's a EFT of large structure, so this has been incorporated there. There's some hybrid versions of this by Nick Cochran. Very popular halo model with baryons, and this halo model has led to this baryonic correction model, where what you do is you take particles in an n-body simulation and you just displace them a bit to match the suppression that you see in the power spectrum. Then using either that model or the hydrosims, then you can build emulators, so like Giovanni Arrico has done, and Mathieu Schaller from Flamingo, or you can do effective parametrization, so just to figure out, okay, what curve can I come up with that mimics the suppression of the power spectrum. The problem is making sure that that works for all simulations and at all redshifts is a little bit tricky. But okay, it seems that there are a few out there that you can use. How do you constrain these models? Well, before KSC, people were using mostly the gas fractions, the X-ray gas fractions in clusters as a function of mass in order to constrain how much baryonic suppression you could get. So this is a compilation from the Flamingo simulation for what was used to calibrate the Flamingo simulation. And then they would consider variations on top of that. So all these curves are different variations of the Flamingo simulation to encompass kind of the error bars that you have on this F-gas. So this is normally what you do. Okay, does it work? Well, let's see. There are other ways that you can get observational priors. So some of the stuff that we've been doing is, for example, you can cross-correlate shear with the diffuse X-rays. So this is Desier 3 cross Rosat. This is work by Tasia Ferreira from Oxford. And what you see here is that there's a lot of signal to noise in that cross-correlation. And then you can try to model this with some kind of halo model for the baryons. And from that, you can try to get the suppression. All right, so this is what we get. So this red curve over here. And it looks like this kind of cross-correlation prefers pretty strong suppression of the matter power spectrum. Okay, this is quite strong. This is in line with the results that Manu showed yesterday for KSC. This is same level of suppression that we prefer. You can add a C as well. That's a super high signal to noise as well, cross-correlation between DES and Planck, and then also the X-rays are folded in here. So this is just shear X, and then you can do all the different combinations as well. And then when you do that, when you do look at the green curve, again, pretty strong suppression of the power spectrum compared to some of the hydrosims. So this is Flamingo, look at this is Flamingo F-gas minus 8 sigma, okay? So you have to really kick out the gas out of the halos in order to be able to match the X-ray and the TSC data. And I think, again, this is similar to what KSC is seeing, a high feedback scenario. Whoops. Okay, similar results now using the Rosita gas fractions. So this is from Michael Kovac, and this is again from Jared Siegel, looking at if you use gas fractions from Rosita, how do they compare to the stuff that has been used to calibrate the hydrosims? And it looks like the new gas fractions from Rosita are also lower. All right, so that means, again, stronger feedback than we've been using in the hydrosim. What is going on? Why are we seeing such a strong feedback in these cross correlations? Is a little bit unclear, because if you look at the KITS and DES lensing results, or HSC as well, that Urosh was pointing out yesterday, there's no significant evidence for such a high feedback scenario. So this is pointing to some kind of discrepancy between how we're modeling the gas for these cross correlations and what lensing seems to be sensitive to. So it could be some kind of selection effect in play, I'm not sure. Okay, so last is photometric redshifts. Photometric redshifts lead to confusion and bias with respect to which matter field you're probing. So normally we try to solve this by calibrating them, either with direct calibration from deep spectroscopic samples or cross correlations at higher redshifts. So this is the compilation we use for kids, for example. But I'm going to propose something slightly different this time. One thing that we're working on within kids is to extend the 3x2 point methodology to a 6x2 point by adding new correlations. So now instead of just having the bright or red selected galaxies, which are still photometric, or you could do spectroscopic here, we're also going to add the clustering of the photometric sample. So all the shear galaxies, the galaxies we have shear for, we're also going to measure the clustering of those and the cross correlation of their clustering with the lensing and so on. Why do we want to do this? Well, it actually leads to tighter constraints on S8 by 40% for stage 3 surveys, and it also gives you a better redshift calibration. You self-calibrate the redshifts by using the extra power of the data. Okay, I think I'm going to skip some stuff because it's otherwise too much, but here you see evidence that a 6x2 point compared to three photometric or three spectroscopic scenario gives you way more figure of merit. And well, in this one, this is just a cosmic shear one. And it's also more robust to how you model the redshifts. So some of these points that are closer here to 0, they're also giving you better constraints on the redshifts. You have to believe me, I'm not showing you that, but you recover the redshifts better. For stage 4, this looks very promising because a 6x2 point cross correlation retains about 90% of the idealized figure of merit if you didn't have any redshift errors. So it's really capturing the redshifts much better. So it mitigates any biases that you might have in your redshift calibration by adding more data. Okay, for many years we haven't been able to do this because doing photometric clustering at full depth is very hard. It's plagued by systematics, survey systematics like depth variations, PSF, size variations across your survey. But we finally managed to get this to work. So we're using an organized random technique from machine learning using self-organizing maps and hierarchical clustering in order to use the information that we have about systematics in our survey to correct the clustering. And we have now demonstrated that this works at the full depth of the kids' data. So this is very exciting, and we're going to do this, we're in the process of measuring this 6x2 point with the kids' data as well. So the fact that these red points lie over here, but then the blue ones are on top of the theory prediction here in black means that we're able to correct for all of the systematics that our survey has. Okay, so I'm going to summarize now. So lensing is a very promising way to probe distances and growth. We're doing that with cosmic shear and 3x2 point. There's still some challenges to solve for stage 4, but we're actively working on most of them. The most recent lensing results are all consistent with Planck. We'll see what the SER6 and the HSC final analysis have to say about this. But for now, everything seems to be consistent, but everything's in flow. This is not the talk I would have given a year ago. And we expect that Euclid and LSST will be very powerful, about 10% constraints on the dark energy equation of states. And to do that, to achieve that, we need to be well prepared. And part of that, I think, is working on these cross correlations to try to really make the most of the data. And since data is already there, let me see if I can leave you with a video of the first look Rubin data. Okay, stop there. Thanks. So yes, so I think probably the photometric redshift uncertainties were underestimated first time to give you the 3 sigma. But it's partly also statistics because we were always at the verge. It was always 3 sigma. So it's partly the photometric redshifts, partly the statistics. Your second question was about what model we should choose, or I think we're going to try different things because, as I said, some models work better on the small scales. Some models try to go fully nonlinear. So we'll have to demonstrate that we have consistency between the results on the large scales and the small scales. That's my personal view of how we should approach this. Mm. Yeah, so it's a Halo model. It's very similar to the Fedeli model, the one that is used by BCM. Yeah, it's very similar to that. Mm-hmm. Uh, you mean in the Dalal paper, there's a 5 sigma? Okay. Uh, I'm not sure. I would have to go back to her. No, if you look at the kits, I have some of that. Right. So this is the kits posterior, and so this is the what you recover for the suppression of the power spectrum from the kits 1 sigma posterior, and it's yeah pretty consistent with 0. I checked the prior. The or prior is wide enough, so we have these extreme scenarios in there. Um, but they're all based on HM code, which is calibrated on a particular set of hydrosims. So it's possible that we're inadvertently having too small a subset of baryonic models. Um, but I don't think it will change the cosmology results, but it might change what we have to say about baryons. Mm. For baryons, yeah. There is a correlation between well, okay, so you're saying that, right? It's a correlation between the suppression and the fraction of baryons. So it seems to be that the only parameter that you care about for the suppression at k, again, k of 0.5, so we're not going very far here. The only one you care about is the fraction of baryons in halos of a given mass, and that seems to do the whole trick. Um, Probably that correlates with some EFT parameter, right? That's my suspicion. Mm, yeah. Yeah, this is being swept a little bit under the rug. So if you look at the redshift evolution of this plot, this is plotted at redshift 0, but if you look at the redshift evolution, different simulations will do different things, because if you have very little AGN suppression, like in Horizon AGN, then what happens is that you have more feedback at redshift, say 0.6, 0.7, but then the halo start accreting that gas back, and so the suppression actually changes sign. It goes smaller. Um, in the scenarios of higher feedback, that doesn't happen. It's monotonic. So it depends a little bit on which scenario. Since we think that Horizon AGM, for example, has too small suppression for what we're seeing in the data, then it's likely that it's monotonic. But it depends a lot on what feedback is at play, whether it's quasar mode or jet mode. And I don't think the people who run the simulations know yet. Right, so this is the line at redshift 0. If you did this at higher redshifts, it will probably still fall in the line as long as you're at low enough K. If you go to higher K, it stops falling on the line, and then you have things moving up and down. I think if you stay at low enough K, it should still fall on this line. Yeah, the line will move, yes. Because the halos that are sensitive to the suppression, so here you have a 10 to 14 mass, right? So that mass will change with redshift. Yes, yes, probably yes, yeah. Mm-hmm. Yes, so some stuff breaks that. Okay, so already at the beyond linear level, you already get B modes from alignments. So they're there. Okay, so so this is already a bad assumption in that sense, because the yeah, with the EFT we predict B modes, right? And we see them in the simulations. They're there. They're small, but they're there. So even in the vanilla situation where you don't have any, anything beyond lambda CDM, you still get them in the nonlinear regime. If you stay linear, then the B modes will appear from the alignments. If you have, say, for example, parity violation, that's one way you can get them. Magnetic fields is another way you can get them. And I don't know, isotropy, I don't know, I'm not sure. But there are ways that you can get B modes, not just one way, yeah. Yeah, so the temperature calibration, I'm not sure. It's very difficult to understand how it propagates to the gas fractions, and I'm not an expert on that. What I know makes a big difference, let me try to go back. What I know makes a big difference is the modeling of the selection function. So which clusters you're getting in X-rays, which ones are bright in X-rays that you're actually using to constrain your gas fractions. And I think some of these older data did not do a good job of taking that into account, but now the Rosita people have good modeling of their selection functions. But yeah, the temperature calibration, yeah, I don't know how much of the error bar is is that. Yeah. Yes. Yeah. Yeah, these error bars are probably too small for, yeah, for what they should be.